You know, when you're just staring off into space, maybe at a dripping faucet, and you get that weird feeling you've seen that shape before? Well, it turns out you might be onto something huge. I mean, really huge. You might be seeing a hidden pattern that connects your kitchen sink to, well, the entire universe. Okay, let's get into it. Just take a look at this. On the left, yeah, that's just a regular old stream of water. But on the right, that's a computer simulation of how galaxies form these enormous stringy filaments across millions of light years. Look at them side by side. The way the stream breaks up, forming those little beads and threads. I mean, it's uncanny, right? It's like the exact same process is playing out on two completely different, mind-boggling scales. So, that's the big question we're tackling. What in the world is the deep, fundamental principle that ties the physics of a simple water droplet to the grand architecture of our universe? The answer is, well, it's an incredible story of scientific detective work that's been going on for hundreds of years. And trust me, this isn't just about faucets and galaxies. This pattern, this whole idea of a stream of liquid breaking up, is absolutely everywhere. It's the secret behind your inkjet printer's precision. It makes agricultural sprays and diesel engines work efficiently. And, get this, it even helps us understand nuclear fission. It's truly one of the most universal things in all of physics. To really get this, we've got to jump in our time machine, because some of the smartest people in history have been scratching their heads over this exact puzzle for more than 5 centuries. And who's one of the first people we find thinking about this? None other than Leonardo da Vinci. And what's so amazing is how close he got. He saw that water has this cohesion, right? An internal stickiness holding it together. But then he made a tiny mistake. He figured the thing that finally snaps the thread had to be the most obvious force around: gravity. And for centuries, that's what everyone thought. It seems obvious, right? Gravity pulls the water down until it just snaps. But here's the thing. When you actually do the math, it turns out that if gravity were the only thing acting on it, a thread of water could stretch for almost 100 kilometers before breaking. No way. The real culprit is something much sneakier. It's not an outside force pulling it apart, it's an inside force trying to pull it together. And that force is called surface tension. So what is surface tension? Well, it's the reason water forms into little beads. The easiest way to think about it is like the water has this invisible, stretchy skin all over it. And that skin is always trying to pull the liquid into the tightest, most compact shape it can, which, for any volume of liquid, is a perfect sphere. Okay, so figuring out that surface tension was the key player here was a massive breakthrough. But that just leads to another question. How does this stretchy skin make a perfectly smooth column of water just spontaneously bust apart into a neat little line of drops? It all comes down to this really elegant process called the Plateau-Rayleigh instability. Here's how it works. You start with a nice cylinder of liquid, but in the real world, nothing is perfectly smooth, right? There are always these tiny, random little waves on the surface, and that's all surface tension needs. It sees those waves and goes, aha, I can make my surface area even smaller if I pull water away from the skinny parts, the necks, and push it into the chubby parts, the beads. This just makes the necks thinner and the beads fatter, which speeds the whole thing up until pop, the neck gets so thin it just pinches off and a perfect little spherical drop is born. And of course, once scientists really truly understood how this instability worked, they didn't just sit back and admire it. Nope, they figured out how to tame it, how to control it with unbelievable precision. And that has led to some seriously cool tech. Just think about the printer in your office. An inkjet nozzle is basically a master of this instability. It's creating and firing out these incredibly tiny drops of ink. We're talking half the width of a human hair at 6 meters per second. It does that by perfectly controlling that natural breakup, making it happen exactly when and where it wants it to. It's amazing. And that's not all. This same exact physics is used for some really high-stakes medical stuff. Scientists can use this technology to print these tiny, precise spots of DNA onto little chips for genetic testing and diagnostics. You can run thousands of tests in a space smaller than your fingernail. It's a total game changer. But what happens when you start messing with the rules? Like, what if you throw another force into the mix? Well, if you hit a jet of liquid with a really strong electric field, you can totally change the game. The normal breakup process gets hijacked, and you end up with these wild, beautiful, almost alien-looking filament structures. It just goes to show how fundamental and how flexible this physics really is.
Okay, so let's bring it all home. Let's close the loop and go all the way back to where we started, connecting that tiny little drop of ink to the vastness of the cosmic web.
And here we are, back at our first puzzle. On the left, that's one of the first ever photos of a drop forming, taken way back in 1887. On the right, our cosmic simulation. When we first looked at this, it was just a weird, cool-looking coincidence. But now, we're in on the secret, right? We know the physics of surface tension is driving what we see on the left. So, what's the cosmic link?
And here it is, the big reveal. It turns out that a long, thin cylinder is just an unstable shape. Period. It doesn't matter if it's a cylinder of water held together by surface tension or a cylinder of cosmic gas and dust held together by gravity. In the water jet, surface tension pulls everything into clumps to form drops. In the early universe, gravity did the exact same kind of thing to those huge filaments of matter, pulling them into denser clumps that would eventually light up as the galaxies we see today. The forces are different, sure, but the fundamental impulse, that deep physical tendency for a stream to break into beads, it's a cosmic echo.
It's just such a powerful reminder that the universe loves to repeat its best ideas on every single scale imaginable, from your kitchen sink all the way to the edge of space. It really makes you wonder, doesn't it? What other huge cosmic secrets are hiding out there, right in front of us, just waiting for us to notice?